tonight, I think we have a great speaker to wrap things up for this
I'm going to go get a chair.
We will have a speaker in July as well, so keep stay posted on the nugget to see who that is, and it should be great. Thank you, Angeline, for the season, for the belfry, for everything you do. I want to thank the usual suspects, the board of the Sister Science Club. David Dern, I don't think David's here yet. Right, okay. He had an appointment, but he will be here soon. Don Betzinger, who's in the back, and he's videotaping this. So thank you. You can find recordings of all of our lectures for the year on our website. So check that out if you missed any. Let's see. Larry Price and Joe Sherry. Larry's here, I know. And Larry is one of the three people, along with Joe and I, who endeavor to try to find good speakers for these events. Dave Johnson is here somewhere. Raise your hand, Dave. Way in the back. Gail Todd is over here. I don't think Jocelyn Blevins is here. No. We have, I think, is Rima Givet here tonight? Where are you, Rima? Hello. So Rima's here representing science teachers in the schools. Thanks for being here. She's also looking for volunteers to help with high school spring birding study this week and next. So you don't have to be an expert. You probably do need to be able to recognize a bird. Talk to Rima, if you will, after the presentation, and I'm sure she can tell you what needs to be done to help. So tonight we have Leif Karlstrom from University of Oregon. Leif has a BS in physics from University of Oregon, a BS in mathematics from University of Oregon, a Bachelor of Music, violin performance from the University of Oregon. And as I started researching, asking Leif to come talk to us tonight, I learned that he's played, I think twice, at Sisters Folk Festival. Unfortunately, he's not going to play for us tonight, but we may be able to get him back to that. He also has a PhD in Earth and Planetary Science from UC Berkeley. Leif studies fluid motions in and on volcanoes and glaciers, landscape evolution, geodynamics. Here's a word for you: petrology. Anybody know what that means? Leif, we have an answer.
Generally, the study of rocks.
There you go. I had to look it up. But the study of the origin, composition, structure, and alteration of rocks and geomorphology. He's also a musician, as I just told you. And he's here tonight to discuss many of the topics having to do with volcanism, fluid, water. Water is very important in this region. In fact, I had a professor in high school who actually was the first person to really interest me in science. And he was very unorthodox. But he told us all, or asked us all, what those single substances, there was one substance that you had to live off of that would give you the longest lifespan with just that substance. What would it be?
Water.
Well, his answer was beer. And Leif, if you're ready, we're ready for you. So thank you very much.
Okay, I have a clip-on mic. I'm sort of notoriously quiet speaker, so this is a good thing. It's definitely a critique I get in teaching. It's but I don't project. It's not a very good quality for teaching, but here we are. Thanks for inviting me. It's really great to be here. I'm going to tell you a story about actually a great lead-in about the most important substance. I'll say that there are actually two fluids that are sort of like the fundamental fluids that shape the surface and evolution of our planets. One of them, of course, is water. The other is magma. And so I sort of live in my research at the interface, I guess, of those two fluids. I study them interchangeably, and it's a bit awkward at times because they are actually fundamentally different disciplines, hydrology and volcanism, but somehow I'm there weaving a path between them. So I'm going to tell you a little bit about, as the title suggests, legacy and future of volcanism on landscapes, water in the Oregon Cascade Range. And so there's going to be what will end up being 3 parts to the talk. The last of which is like squarely focused in this region around systems, which is why I was happy to get the invitation to talk here, because I feel like it's relevant and hopefully interesting to you all. And I'm happy to answer questions at any time. You can, of course, like interject and yell at me if you want, or you can wait till the end and won't mind. Let's get started. As was mentioned, I do have a side of my life that is musical, and this is going to be the only time that features in this talk. But it's something that I'm quite interested in and have a whole side to. If you're interested in that, yeah, please check this out. But I think it's a nice way to sort of subversively get you interested in science, even if you're not a scientist, even if you don't know how to read a graph, scared of math, etc. Music elicits an emotional response, and so it's sometimes fun to listen to data, because not only do you feel things when you listen to data, but your ears are these amazing sensors that detect patterns in kind of a very efficient way. Tell when something is whizzing towards your head, for example, and they actually have much better resolution in that time domain than your eyes. So as sensors, perhaps as scientists, we should be using that capability. So I've been quite interested in the general approach to representing data through sound. So what we're going to do is we're going to listen to some data that's relevant to the talk. It's actually probably most relevant to the last part of the talk, again, this bit. That's kind of about the Central Oregon Cascades. But I'm just going to play. It's a video, so I'm not going to talk. It has it sort of set up, gives you a guide to what to listen to. But to set it up, right, we're essentially thinking about water. We're thinking about water in the context of volcanoes. We're thinking about the legacy of volcanoes in this landscape. And as it turns out, as the volcanic rocks, those lava flows and so forth, age, water moves through them and on them in very different ways. And so we can learn a lot about that structure by looking at how water moves. And so that's what we're going to listen to. Actually, I'll just pause it. These are two places. If you haven't been there, most of you probably will recognize this, but this is just west of where we are. This is Clear Lake. There's a USGS stream gauge there. And then down by the town of Blue River is the H.J. Andrews Experimental Forest. They're both along the Kingsley Highway. And right next to each other in some sense here, just a few miles apart. But they have very, very different character, and we'll talk about that. This is the creek in the H.J. Andrews Experimental Forest. Here's Clear Lake. So they have sort of different voices, and you can listen to them playing with each other. So it's 1 year of water. And the rivers respond when it rains. So you hear that sort of wah-wah effect. And the rivers go response to the rainfall or snowpack. Graph on the top left is showing you the discharge, the one on the bottom is showing you the precipitation. So when it rains, you'll see the get color. So the fact that it's very dissonant is telling you that those streams are behaving quite differently to the precipitation. And that's going to be important there. The graph on the right is a little bit technical, but I might as well explain it a little bit. It's a plot of the discharge against the change in discharge. And so the slope of that line actually tells you something quite fundamental about how the streams are responding to precipitation. It's sort of standard school hydrology. They have different slopes, so that's telling you that these two streams right next to each other are doing really different things. And it happens that they're in rocks at different points. Okay, so that's the thing. Yeah. Fun. All right. That's all we're going to listen to music. It's a good talk. All right. So I guess the idea, though, right, is that we're both, I guess, in the element that we were bringing out, that kind of like dissonant element, but then also visually, like on that recession curve or just on the plots themselves, these sort of records of discharge in these streams versus time. We call those hydrographs, and they're quite different. Those are two stream gauges that are not very far apart, and we're going to sort of tell a story that these things reflect, in some sense, the volcanic legacy of the landscape. So that's where we're heading. That's kind of the end of the talk, but I'm going to build up to that by kind of first, I guess, giving you some context about the Cascades as a whole, and sort of the building of the Cascades in terms of volcanism. We'll then do a bit of a case study. Part one is we're going to build the Cascades art. We're going to learn from volcanic topography what we can sort of infer both about sort of the deep processes that we can't see and the time evolution over millions of years, really, of the Cascades art. Part two is we're going to do a bit of a case study in the Columbia Gorge, so border of Oregon and Washington's, the Columbia River, crosscuts the Cascade Arc. It's actually the largest river in the world to cut across a volcanic arc. And so that gives us pure erosion, these really unique constraints, also on the role of volcanism. And then we're going to kind of, in the last part, zoom in back to Central Oregon and come back to the water and ask what can we learn. I'm going to use this term, the critical zone, which you may not have heard before, but it's sort of a, I guess, all-encompassing moniker for this interface between surface processes, the atmosphere, and the solid Earth. It's where all life exists. People call it the reactive skin of the Earth. And I've recently become quite interested in the critical zone and volcanic landscapes, which, as it turns out, are fairly understudied compared to other terrains. And so that's kind of one of the things that makes this region special. It's this volcanic critical zone. And so we'll talk about that. All right. Diving in, I guess, will take us all the way back to 1880 and thinking about what volcanoes are. It's not a trivial thing. It's kind of one of the big, deep earth science questions, right? So this is a quote by Dutton from 1880 that says, each volcano is an independent machine made, bent, and monticule that is for the time being engaged in its own peculiar business, cooking, as it were, a special dish, which in due time is to be separately served. So of course, it's the three sisters here, so a nice way to start the talk in some ways, but these are deep questions, like what is a volcano? What are the sort of deep processes that lead to this kind of very spectacular and characteristic topography that we see in the Cascades? And so I guess to start to answer that, let's zoom way out And I'll show you here, right, this is the topography of the Cascades arc from California to the Canada border. Of course, the Cascades goes into Canada too, but we're just plotting up to the Canada border here. And, right, probably goes without saying, especially to this audience, that volcanism defines the topography of the volcanic arc. Around here, every little hill that you see, every high peak is a volcano. And so it sort of defines the mountain range. It's what built the Cascades. But there's some subtleties to it. And if I asked you this question, right, how many volcanoes are there? That's actually not so trivial. Turns out there's thousands, actually. Not just the big ones, but there's all these sort of little ones interspersed between. And so then the follow-up to that is this question: can you identify the volcanoes or the characteristics of these landforms on the basis of topography alone? And that was actually the research question that we posed to ourselves when we were starting this work, and I'll show you why that becomes important shortly. Because ultimately, right, we want to answer this final question, which is, what can we learn by just looking at the shape of these landforms about the subsurface, in some sense, right? The magma that sort of erupts at the surface takes this long path through the crust that's largely hidden from us, even with our best current methods. So we have to use all the tools we have, and topography was one that I kind of got interested in, and it turns out there's some things that we can learn there that hadn't really been recognized before. So that's kind of been a fun journey. To take a next step, I'm going to take you on a sort of aerial tour of the volcanism of the Cascades. We're going to start in the north, and we're going to fly south. And so there's this perspective view here. We're looking from Mount Baker south. Each little red dot on there is a vent that erupted in the last 2.5 million years or so. It's called that the Quaternary epoch, the period. And so as we fly south, you'll see that the characteristics of the volcanic arc change really dramatically. So this is the northern part of the Cascades. We now move south to around Mount St. Helens. There it is. I don't know if it's right now, it's not, but over there. Mount Adams, of course, there to the east. We're looking south. You see the Columbia River Gorge. There's that gash through the center. There's Mount Hood. And you can see there's lots more volcanoes, right? Lots more red dots. So there's some sort of fundamental shift that's going on as we go from north to south. And then if we go even farther south, now we're looking here in central Oregon, right? You see Sisters, you see Newberry there over on the left, and we're just
Is Newberry part of the arc?
Yeah, I mean, people argue about this. Yeah, I would say yes. I mean, some people say technically it's like the back arc, but it's still Cascades. Newberry has some funny things about it. There's a sort of rich legacy of volcanism associated with the subduction zone, which is this line of volcanism that parallels the plate margin. But as it turns out, there's some other stuff that kind of comes to a head here in central Oregon. There's a lineament of faults and magmatic activity that actually trends down to southeastward, which is the origin of the Yellowstone hotspot, and the Snake River Plain and all that. So there's kind of some neat things that are happening here that are a little unusual, and Newberry kind of sits in that place. So people argue actually whether it's strictly Cascade arc or not. It might as well be for the purposes of this time. It's right next. There's lots of little dots, though, right? And so this is this really fundamental difference between the volcanism in central Oregon and that farther north. If we go farther south still, now you see Crater Lake there, and then you see Shasta and Medicine Lake, and that's the southern extent, our Lassen of the Cascades. And again, you see a lot of these little dots. So there's this very strong gradient north-south in volcanism. You can see just by looking at the topography, looking at the plants. And so here's all of them in a sort of compilation in some sense. And one thing to just highlight, going back to those questions that I was posing to you, is there's a huge variety of different types of volcanoes. Yes, there's sort of like these little cones that sit in the landscape, but from cinder cones to these big sort of monolithic stratovolcanoes, the calderas, and lots of other stuff too. And so, this question of could you distinguish these features for topography alone is like a little bit less trivial than you like. And in particular, the angle that I'm going to take on it is that we actually want to teach a computer to recognize these things and pull them out of the landscape. And if you pose it that way, then that's actually a much harder question. You don't have to be able to state things in a very precise way that you can put into a program. But we've done this, I think, with great success. So here's Newberry. We've come up with this sort of semi-automated procedure for extracting volcanoes from these things called digital elevation models, or DEMs. And the results of that, and I'll sort of give you a sketch of how that works. The results of that is given here on the right, that we can basically extract outlines, the sort of basal contour of all the volcanoes in the Cascades, and there's about 3,000 able to find, which is kind of neat. One of the things that we can do with this, and in part, I guess, sort of like briefly taking off the hard science hat and sort of putting on the artistic hat, I guess, is how do you represent these in an interesting and compelling way? This is just what they look like, right? The net result of this essentially is a machine learning approach that we use to extract volcanoes from topography. Can we sort of show the patterns here in an unexpected way that maybe tells us something? And so I'll suggest that there is, if we sort of expand them out from where they actually sit, all clustered on top of each other, you really get a sense for just how many there are. And this, of course, is Central Oregon. This is Newberry over here to the right, and the Sisters and all the little Blackboots right here, etc. And so you can really see how many volcanoes that we're talking about here. Pretty cool. And if we do that for the whole Cascades, you get something that looks like this, which is definitely not the normal way of looking at topography, right? So, artistic license or whatever, but it gives you a real sense for this fundamental transition. Of course, it's on the side. So north is to your right, and so that's the Canada border here on the right, and like Lassen down here on the left. You really get a sense for what it means to have these volcanic centers and all the clustering of these.
Is the top one, is that heat sensitive?
Heat sensitive.
I mean, why are we seeing them as light and dark?
I guess it's a grayscale of elevations, yeah. So the lighter the color, the higher the elevations. And then the bottom one is just a sort of fancy representation of the same thing. So shaded relief version of the same thing. Just looks pretty.
So can I just be clear, the quaternary vents are those little dots all over?
Yep.
And they're not visible to us looking?
Well, they are, of course, but they're all jumbled up. They're all superimposed on each other. And so this is just a way of kind of like pulling them all apart and saying, hey, they're all here. Yeah. So the physical locations of these volcanoes are not what are plotted. It's just a way of visualizing it. They're kind of like as close as they can be without overlap. Yes, it's all right. And so I guess to take this, why not a couple steps further? I got sort of inspired by these really old illustrations. You find these things in like old atlases, 18th century, 19th century atlases. And it was kind of before we had a good sense of topography or real precise ways of measuring things. And so you find these illustrations that are like, comparative views of mountains and rivers, and they would look something like this, and they're all sort of jumbled together, and it's like, there's definitely some artistic license going on in here, and it's quite dramatic and cool. And there is some degree of accuracy, and so I guess what we wanted to do is say, like, let's do this same thing, but using real data, using digital elevation models. And so we've done this, and we actually won an Atlas of Design competition for a result of this that you can look at. I didn't actually include it, probably should have. But basically the idea is that we take our grayscale images of the heights, and we do some fancy, shaded relief magic and various software that's out there, free software, so it's not it's accessible to anyone. But this gives you a new perspective and a new way of looking at things, and in particular, this is one of the cool ways of doing it. Here's all the Cascade volcanoes that we found so far. They're all lined up like a coin, right? And they're ordered in terms of height. And so, the highest ones to the lowest ones. And I guess one of the things, I guess you can sort of appreciate in the representation like this. There's Newberry again, right? There's Crystal Lake, etc. But I guess one of the things you appreciate in the representation like this is that all the volcanoes that you think are volcanoes, like if you were to take an airplane and fly from San Francisco to Seattle or something like that, you would see these big peaks. And that's just really like the first few entries on the top row. There's all these other ones. Many of them, like I said, are just every single hill that you see around you is one of these. And so it's kind of a cool way to just sort of represent this landform. I think it's quite beautiful, but of course we want to do science with it, so I better tell you about that. So first I'll tell you about how we made this. We teach a computer how to recognize volcanoes with the sisters. A nice local example. And so the idea is we start with a digital elevation model. We also start with the known locations of events. And that is not required, but certainly helps us out a little bit. There's been decades of work by a lot of people going out there and mapping these things and dating them and figuring out where all the events are. So that big database that I showed you is not my work. I'm not taking responsibility for that. We're leveraging that to sort of extract these landforms. So how do we do it? So you basically come up with an algorithm. You say, okay, well, a volcano is basically some sort of cone-like-ish thing. We'll draw a closed contour. And then we'll sort of correct for the fact that it might be sitting on some sort of slope, and so extend the rays down from a assumed summit, and then you can kind of extract the closed contour that represents that volcano. And that result of this is what's shown here. We do pretty well, actually. We can kind of, in an automated way, extract the basic contour of all the sisters volcanoes, including ones that are sort of superimposed on each other. Ends up being, we don't get everything for sure because there's a lot of complexities that turns out in volcano shapes. And so that's just, that's how science goes. You think about the next iteration of this next time around. We get about 80% of all the volcanoes that are extract the contours. And doing that, we can now do science and say, well, how much volume is included in that basal contour? Why is that important? Well, that volume tells you how much magma, in some sense, came out. It's not everything. There are eruptive products, lava flows, pyroclastic flows, ashfall, all this stuff. In some sense, the size of the edifice is a pretty good proxy for how much stuff came out over the lifetime of that event. And so we can just simply sum up the volumes. We could do that, thousands of these things over the whole Cascades, and we get this, which basically tells us not only the type of volcano, because we've sort of classify them in some sense based on their shapes, but also the volumes. So this is telling you, right, it's kind of a complicated graph, I guess, but the total volume is on the bottom there, and it's as a function of latitude. So evidently, it's not uniform at all, the extrusion rate of magma along the Cascades. They're kind of like these hot spots. And one of them is right here in Central Oregon, this peak right here. And if you look at the types of volcanoes involved, that's one's interesting too. This is another way of kind of looking at that coin book, which is that all those tiny little ones, those are all cinder cones, or scoria cones, I guess is what people like to call them now. And they make up the vast majority of all the edifices that exist, over 2,000. Right? The composite volcanoes, the things like the Sisters or the Hood or whatever, those are much fewer. But they're also the big players in terms of the volume. So there's kind of some interesting things to think about there. The total volume of these edifices ends up being about 2,700 cubic kilometers. Remember? This ends up being comparable to things that people have estimated based on sort of other considerations where you're trying to not just get the edifices, but all the products, like the flows and all these things. We're not addressing that at all. We're just sort of picking up the volcanoes themselves. But we get roughly half of the total Cascades extrusion in this approach. And so basically we're sort of saying that the volcanoes roughly, if you consider this at an arc scale, the scale of the whole Cascades, represent about 50% of the total output, which is kind of neat. That's a cool result. Of course, knowing where the volcanoes are, knowing their volumes, we can also now ask questions about how they relate to superstructure, okay? And so there's a lot of data that informs this subsurface structure in the Cascades. Again, decades of research in a whole lot of different contexts. And so I won't bore you with all of it, but just to highlight a couple. We have heat flow. So this is a really cool map. This is from a compilation that's a bit old, but it's still pretty much the best that we have. And you see that there's more heat coming out of the ground from the volcanoes, but also there's some geologic provinces here that we can pick apart and go into that. There's basin, range, cascade subduction, so on. It's all sort of there under the heat flow. Another one that we think is quite interesting is to look at sort of so-called seismic tomographic images, sort of like getting a CAT scan. They're doing this of the Earth. We use seismic waves to make images of the subsurface, stuff that you can't see. You can see maps that look like this. Seismic velocities that you infer some sort of mixture of how hot, which is typical, and what composition. So there's basically like, you see these anomalies, these little red and blue blobs, and those things are telling you at different depths. It's sort of a complicated map, but I guess just to sort of highlight, you get these blobs. And they tell you something, right? And so we compile a whole lot of data like this. Again, we want to compare it to where the volcanoes are. We want to ask, what do these things tell us about that sort of subsurface dimension that you can see? And here's in some sense what you get. It's a bit pixelated, right? But there's a whole lot of data that's like, you have measurements of gravity, you have measurements of heat flux, you have sort of ground deformation from sort of intraseismic period between the great earthquakes, which is where we're in now, and then you have seismic tomographic results. And we can now compare those to the vents. And in some sense, right, I'm going to sort of stop there. If I go farther than this, it starts to get a lot more technical. But basically, we were able to sort of show that the Cascade vents, especially the young ones, overlie these kind of anomalies, things that you would sort of expect are matching where magma is. So it's kind of mapping out the subsurface in a way that we're like looking for something in particular. And of course, we're interested ultimately in really mapping out those structures, the pathways of magma through the crust, where it's going, especially how it changes in time. This is a step towards it. It's a long-term sort of grand challenge goal, but here we've taken the first cut of it. We've taken all this sort of geophysical data, which you see on the left, compared to topography. And we can basically say that they correspond, and that's great. And that gives us a step forward. So let's stop with that. The sort of conclusion for part one, that's the sort of regional context. Right? Now all these volcanoes are sitting there on the surface. They seem to track something that's going on the subsurface that's telling us about where magma is. And sort of expects where magma is, there's higher heat flow. There's lower seismic velocities. You go through each one of these things. But I'd rather do that in the context of a case study, and so that's what we're going to do. So this is the next two parts of the talk, very roughly, are going to do these little case studies. Part two is going to be on the Columbia River Gorge. You can zoom in there here for a sec. And then part three, we're going to come back here to Central Oregon and talk about that. Here's the Columbia River. It's a pretty cool river. It's the largest river on Earth, like I said, to cross-cut the volcanic arc. It's also one of the steepest rivers of its size in the world. Lots of cool things about it. This is what the drainage basin looks like. It's up in Canada. Covers most of Idaho. Columbia Gorge is this little area right here where it crosses the Cascade Arc. So that's what we're going to focus on. We zoom in on that area. Here it is. Turns out there's some interesting storytelling to do here too. The Columbia River has been quite dynamic over time. It's actually been around, it's been cutting through the Cascade Arc for like tens of millions of years, at least 20-25 million years, which is, at least half or quite a bit more than half in some sense of the whole lifetime of the Cascade Arc. And right over that time, lots of stuff has happened, including the Columbia River flood basalts, which we're not going to talk about at all. Started the Yellowstone hotspot tract. And the Columbia River, as a result, has kind of been pushed around. And this is a manifestation of that sort of competition between magma, lava, and water. It's like the sort of basic competition between these two fluids that are shapes of the planet. And so you can sort of see that in the where the river goes. That you see this old river channel cut through. Actually, if anyone's been to like Silver Falls State Park, beautiful spot, lots of waterfalls. That's all Columbia River flood basalt. That's actually the old channel of Columbia River. From there and it popped out at spots. That was where Columbia River used to be if you were here 16 million years ago. But it got pushed north from the Columbia River flood basalt and kind of established this channel here, more or less where it is now, but not quite. And so there's kind of been some jostling around of the Columbia Channel. And in particular, I guess the one that we kind of focused in on is this most recent, what we call Paleo Channel, which is the spot where it used to flow, that it got abandoned at sort of roughly 3 million years ago, 5. And we know that because it's now exposed in the walls of the current Columbia. So we had this whole project for a while looking at this and got some permits from the Forest Service and got to fly a drone up there. And so one of the things that we'll see is going to be a video basically from a drone looking up a tributary to the Columbia. So in some sense you can sort of, in this image, you'll see it because it'll pan around. But the Columbia River is behind me, so we're kind of looking south, up one of these very steep drainages on the south side of the Columbia. And one of the things I'll draw your attention to as we're moving up here is there are all these stacked lava flows. Those things are going to be front and center in our third part of the talk. We're talking about how water flows. But those are Columbia River basalts. What you see up here is this orange layer. That's the Paleo Channel. And that thing got filled in by what's called hyaloclastite, which is a type of rock that forms when lava or magma interacts a lot with water. And so here we go. It's a creek fire there, some burning trees. This is Columbia River. Okay, so we were studying these channels, and you might ask, well, why is that Paleo Channel like so high? Turns out that's sort of why we were interested in this. It's been recognized for a long time. Actually, there's sketches along these lines that go back to the early 20th century, where people are basically tracing these Columbia River basalt layers and noticing that as they go through the Columbia Gorge, they kind of go up, like bend upwards. Right, so they have this kind of arcing shape called an anticline. And so Hood River's over here, so east, Portland's over here. To the west, Sandy River is right there. These are the Cascades Arc is right in between. So it's kind of interesting, right? That the basalts are bowed up, right, where the volcanic arc is. And so that kind of is what got us excited about this. And so we based a whole study around trying to figure out what's going on with that deformed layer. And it ended up being a pretty cool story. So if we look south, we're just kind of same shaded relief perspective as before, but we're now just focusing on the gorge. So this line here is the Columbia River, and then this little dashed line here is the approximate location of those Paleo Channel deposits, which is a good sort of proxy for what used to be flat. This is kind of what you could use the lava flow too, but the river channel, Columbia River Channel is pretty graded and pretty flat here, so it's a good sort of like strain marker thing that you can use to track information. So we're going to use that layer to sort of see what's happened since that channel was abandoned about 3.5 million years ago, and it's been uplifted almost a kilometer, right in the center. There's also kind of some interesting things with these faults that are actually both manifested in kind of Hood River area, the Hood River fault zone, but also in the Portland Basin. These normal faults that are kind of enigmatic, and we're going to sort of propose an origin for them too. Everything kind of fits together. But I guess one of the reasons that this follows on nicely from the previous part of the talk is that we were able to bring in that subsurface data in a nice way. So here's that. Basically, every data set that we can find co-varies with the uplift. And so I'm now representing that uplift here. This is kind of some data, various types of data, and then like a model fit, which I'm not going to talk about too much, but basically we're able to model this deformed layer as simply like an elastic plate kind of pushing from below, which is kind of cool. But everything we can find co-varies with that budging deformation. If you look at heat flow, that same data set that I showed on the Cascade arc scale, this thing called gravity, which measures sort of variations in mass or subsurface mass deficits in this case, probably from hot rocks. as well as seismic velocities and the distribution of earthquakes, and that's this bottom panel here. So kind of similar to what I was showing before, except in a depth slice now. So the surface is here on the surface, and you're sort of looking all the way down to 35 kilometers, basically the depth of the Earth's crust in this region. And the hot colors that you see here are seismic velocities that are like slower than average, meaning that we have some reference model, and the seismic velocities are anomalous, much slower. Likewise, the bluer colors are sort of faster than you expect based on this reference model. And why that's interesting is that slow versus fast maps pretty well onto temperature, you know. And so if you look at the slow ones, the only way to get these really distinct slow velocities is through magma, which is pretty cool. And that white contour actually is some quite detailed modeling that's arguing that you actually need partial melt of a certain fraction basically to explain the seismic velocities that you see. And so what that's saying is that like right now as we speak, there is magma underneath the Columbia Gorge, which is pretty cool, but it's at 30 kilometers depth. Right. Also, it's right underneath these anomalies, both of the long-term deformation, but also the heat flow, the gravity. So like it all is kind of fitting together in a cool way. If we look at it in map view, this is I think sort of a very compelling, cool plot. These are sort of the same seismic tomographic images, but done now right in map view at different depths. So I drew a line here at 20 kilometers and projected it from the south and to 25, 30, 35. These little triangles are the big stratovolcanoes. There's Mount St. Helens, Mount Adams, Mount Hood. What's cool about this is that you sort of see, as you go from 20 to 25 to 30, you get this kind of like elongated structure that sort of like connects Hood to Mount St. Helens. And that structure is what you're seeing here, right? It's like the white contour. And so it's kind of neat, right? It shows that there's sort of this probably magma-filled, not totally liquid magma, so I don't want you to picture like a big pipe filled with magma down there. It's not quite that, but there probably is some fraction of magma in this sort of conduit-like structure at great depth connecting Mount St. Helens to Mount Hood. Fun fact. Okay. So if we go back to the gorge and this question that we had about the arching deformation, we can kind of start playing some similar games that we did with the volcanoes at the kind of regional scale. Right? And we can sort of say, well, we now have a basin, right, with this arching paleo channel that once was flat, but now has gotten bowed up. And so we can kind of just take the modern topography and pull it off and calculate the volume very simply. Right? And so we're basically going to take the area between these two curves. This one is a sort of a swath topography showing the current peaks of the Cascades sitting on top of this deformed layer. And so you can go ahead and calculate how much volume is underneath that curve, which tells you how much magma has pushed up the layer, and then how much volume is above that curve, which tells you how much is erupting. So you get that ratio, and that's kind of interesting. That's not an easy number to get. We have direction constraints here. Notably, this one is really hard to get. It's intrusive flux rate, which tells you sort of the deep flux of magma into the crust from the mantle, and we get this number here, roughly 10 cubic kilometers per million years per kilometer, because it's in a cross section. The ratio of the two, I don't think I have that on these slides, but it ends up to be about 3 or 4. So in other words, 3 or 4 times more intruded magma than erupted magma, which is kind of neat. That's a good rule of thumb to have. It's probably a lower bound, actually, almost certainly a lower bound, as I can talk about, but it tells you that there's a lot more magma going into the crust than is expressed in the topography. So neat things we can do. Other things we can do, here we go. So this is kind of putting some points on that here. The middle panel, panel B, is kind of what I was just showing. Basically, the difference to the red curve is if you remove the intrusive uplift, kind of that bowed thing. What's sort of interesting about this is if you look at where the volcanoes are, and I don't have all the little dots like we did when we were doing that overview when we were flying from north to south, but I have kind of a smooth version of it. If you want to think about like higher concentration of vents when this curve goes up. This is sort of a kernel density function that measures the density of those vents. And what's kind of neat is that they have distinct peaks here. So Mount Hood would be involved in here, but also a lot of the smaller edifices around it that would be the monogenetic things and so forth, or silicons. They don't actually line up with the peak of the bowed up deformation, which is interesting. Maybe you would expect that, maybe you wouldn't, but they're off. There's sort of two peaks, one on either side. And one of the sort of satisfying things about going through this exercise is that we think we can kind of explain why that's the case, and it's all has to do with why that deformation is there of the paleochannel in the first place. Is that if you kind of conceptualize the crust as like an elastic plate, like I was saying, pushing it up from below with all the magma coming into the crust, it bows up in this manner, but the stress distribution in that plate has a very characteristic pattern. In the bottom of the plate, you can imagine you're pushing it up, so it's like in compression, and the top of the plate, you're pulling it apart, it's an extension, and there are these maxima and these kind of places where it switches from compression to extension. And what's kind of neat about this is that the place where it switches, where you basically see these inflection points, lines up pretty dang well with where the peaks and the volcanoes are. So we think that the volcanoes are exploiting these weaknesses that we get. We also think that's why the Hood River Fault Zone is there, and it kind of all fits together in a nice way. Predicts basically where the boring and volcanic fields are, which are these kind of enigmatic, off-arc volcanic fields. One of them is the City of Oregon, on the boring volcanic field, and then Simcoe is off to the west. Okay. So that's conclusion number 2. Story number 2. We did this sort of case study in the Columbia River Gorge, and really what this thing is highlighting is these interactions between magma and lava. There's a whole other side of this which I could get into about how rivers cut those channels and the disequilibrium that one sees, and I'm going to talk about that. But it's all intertwined in a really cool way. The basic takeaway is that mountain building in these settings in the Cascades really is driven mostly, right, dominantly like 3 to 4 times more by intrusive stuff that you never see erupting on the surface, but it's like coming in and pushing all the floors. Cool. All right. Part 3. We're getting through it. Let's move down to sisters and come back to some images I showed at the very beginning. Let's sort of dig into this a little bit more. On the left is topography, so familiar now. On the right is the age of the volcanic rocks, and that's something that requires a lot of work to get that, like the one on the right. The one on the left we can basically get from satellites these days, and it's relatively easy. The one on the right requires detailed geologic mapping, dating, and refinement of those things over a long time. So it represents a whole lot of work. But we have quite a detailed map here of this region. And of course, I think the things to highlight is that where the active volcanoes are. These sisters, those black peaks right there, hard to recognize a lot of these things. That's where the youngest ages are. Stands to reason, right? Like the youngest ages where stuff was erupting most recently is where we see the active volcanoes, but it's all volcanic, right? Like from here to Eugene and beyond is volcanic. And that's because the volcanic arc has migrated east over sort of tens of millions of year timescales. Like if we were in Eugene 30 million years ago, the arc would be there, all back in like Spencer's Butte or whatever, like that is the remnants of the little shallow intrusion that has an age of about 33 million years. So that's shown the progression of volcanism over time. And so what's really cool about this is that we kind of have what we call like a space-4 time experiment. If you sort of go west from here, the rocks progressively get older. If you go east from here, that's true too. It's a little bit more complicated, but you kind of have this neat strip that varies largely with longitude, position west to east, that's tracking the age. And so that represents to us a very preliminary experiment, and also sort of is striking when you look at other data sets. And so maybe one theme of this talk, if you like, apart from the odd data representation stuff, is I like to compile data of various types. And so here's a whole bunch of stuff. Same things as before. The left is basically topography, the right is basically ages, but we've overlaid on top of that a whole lot of other things. Rivers in the region, we have places where now we're moving water, so stream and spring gauges occur. Some of these have been measured by our group, some of them by the USGS. We've been doing this for decades and doing a great job. Lakes, since this is a contribution of our study, there's over 1,000 lakes in this area. All these little dots, right? There are little lakes that we can see via satellites. The size of the dot corresponds to the surface area of the lake. And then on the right, we have a lot of other stuff. We have the volcanic vents, so that's the data set that I described. That's all the black triangles. And we also have these yellow stars. And those things are actually geothermal exploration drill holes and wells. And we'll talk about those. They're going to feature pretty strongly here, too. But safe to say, we know a crap ton about the Cascades in this area. And so if you take a cross-section of pure mass, which is possible, again, because of the detailed mapping, and in some sense because of all the exploration drilling that was done, we do have a sense of what the subsurface structure looks like here. And so this is this box, this pink box here on the top. You can sort of project that down. Like, we're not going nearly as deep. We're only going sort of a kilometer into the earth rather than 30. But this is in a lot more detail what's going on in the backyard. There's a ridge, more or less. Black bead is actually that little bump. It's there, but we're averaging. So it's smaller than so don't get upset because it's and Santine Pass is here. Kinsey River, Metolius. A lot of sort of touchstones here, right? But things to kind of take away, I guess, is one, here's this age map, so going from west to east. The age of the volcanic bedrock on average is given by this black curve. So it goes from sort of over 10 million years in age to less than about 1,000 years, a couple thousand, just lava flows in this region. And that defines what we sort of colloquially know as the High Cascades province, and then the Western Cascades is that older stuff to the west. And so basically what we were after in this case is to tell the origin story of those two provinces. You sort of see them, certainly as you drive through the region, the nature of the landscape fundamentally changes. Out here, it's sort of flat, you have, I guess there's vegetation and stuff, but not a whole lot of deep river channels. And as soon as you go east, as soon as you go west from here, down to like the town of Kinsey Bridge and west from there, all of a sudden you're in this very highly dissected, very steep topography, ridge and valley topography, right? And again, it's kind of like the other thing that we're sort of noticing in the Columbia River Gorge is that like once you start noticing that pattern, like everything varies with position, and we're going to say that it varies with age. And that's going to be a controlling factor. Somehow, it's that the age of the volcanic bedrock is dictating all these other changes that are going on. Last thing I'll call your attention to is like a very busy plot. This panel D here is basically taking these holes, these red lines, which are the actual depth extents of the drill holes in the swath, and then representing the temperature gradient as these different colors. And I'll have a slide on this in a bit, but it's kind of, ends up being a pretty important point that basically yellow are what you might sort of expect as what the temperature does as a function of depth. It basically should increase. It gets hotter as you go down into the earth. And that happens for these ones over here on the left. For the ones in the High Cascades, particularly this one here, the Santine Pass hole, which is pretty deep, it's about a kilometer deep. It doesn't do that at all. In fact, it's isothermal. The temperature doesn't vary with depth at all. In some cases, it actually goes opposite. It gets colder with it, which is odd. People, this is why these were geothermal exploration wells and not production wells, is because basically they're useless for geothermal energy. They call this the rain curtain. Because turns out that that's how you get these isothermal temperatures, is the water is sweeping that heat down into the earth. So you won't get the geothermal heat that you might expect based on all the volcanoes. That's going to be important. Right? What we're going to do now is we're going to basically take everything that's on these two plots and collapse it down into one line. So here we go. If we take everything in that top panel A, meaning the topography, and in this case the rainfall, it's preset, that's what it looks like. So we have this big orographic effect where all the rain is kind of trapped here on the western side of the Cascades, not so much in systems. And then over here on the right, we're going to collapse all the ages down to this one curve. That's a mean, that's a range. So it's a dip right where you see the highest topography. And we can now do that with all the data sets. Okay, so here it is. Those top panels you just saw. And then there's a whole bunch of other stuff. The panel C is basically the drainage densities, the measure of how steep and dissected the topography is, how many river channels there are, how many sort of kind of U-shaped valleys and steep hillsides and things like that. And you can basically see that there's this nice sort of uptick in that drainage density and mean slope as you get to the Western Cascades. All the lakes are basically tracked here at the top, so right where we are now. Lake number density. This bottom one, or I'll do the bottom one first. This is that rain curtain, the isothermal length of drill cores, so that sort of region where the temperature doesn't increase with depth. You can basically extract how long that is and plot it as a function of longitude, and it upticks right here too, which is cool. This middle one is something about how the water behaves, and so I'm going to spend a little bit of time on that now to kind of pick it apart, but just to give you an overview. Basically, if you look at all the stream gauges that you can find in this region, and there's quite a few, several dozen of these things, both springs and streams that are monitored. The gauges on streams that are sort of pretty far west in this Western Cascades province are very runoff dominated. When it rains, the water level goes up. Stops raining, the water level goes back down. This takes us all the way back to that sonification that we did at the very beginning, where the distance and the hydrographs go up and down. That's what's controlling it. It's rain or snow, water goes up, stops, goes back down. We call that runoff dominated. The ones that are up here in the high Cascades don't do that. They're basically constant year-round. So what's plotted here is basically the mean annual discharge range. So how much does the stream flow vary from minimum to maximum over a year, divided by the average for that year. And that's by the average to normalize between different sizes of streams. So you're just looking at the behavior between those different things. And what's pretty cool about this is that these high cascade streams, you see a value of 10 to the 0 or below 10 to the 0, meaning that the range of discharges is basically equal to its mean, 10 to the 0 to 1. The range per year is not very much, whereas over here it's kind of order of magnitude higher. So we'll come back to that. But right, that's in some sense what it means to be a spring. Think about it that way. Okay. So the whole story that we're telling here is basically a story of how aging volcanic bedrock influences all these factors. So this is really the sort of like legacy of volcanism, because this region, especially as we go west, hasn't seen volcanic eruptions in a long, long time, and so as a result of that, the rocks age and weather. And so we're going to basically, the long and short of it is that there's kind of two different provinces, the high Cascades and the western Cascades, but they're going to map onto these processes. And we're going to bring back in this term called the critical zone, which is basically just like everything to do with how water moves through and affects everything. Right? So both alteration of rock, sort of petrology, whatever, but also life and vegetation and all water resources and everything like that. Right? So there's this young Cascades critical zone that's basically defined by the young volcanic ages. There's a lot of details on here that I'm not going to get into, but the long and short of it is that the young volcanic rocks have lots of fractures, and then they promote vertical infiltration. And so it's easy for water to dive deep and eject away that heat. That's why we get those isothermal drill cores. As soon as we get past a certain point, the rock sort of weathers, and those fractures close up. It could be through clay formation, in situ weathering, or it could be from deposition of particles from a few different sources, but those pathways, those permeable pathways go away, right? And so the landscape sort of transitions fundamentally from one where the water seeps in and goes down deep to one where the water gets pushed laterally over the surface, and then it starts eroding, and you get a whole different type of regime. So how do we know that that's the case? Well, we can actually look. So this is a tomographic image, kind of the same as I was talking about with the seismic tomography, but here using electrical resistivity, kind of similar principle, but we're sort of mapping differences in resistivity at the scale of a lava flow. And so this is a picture of that lava flow, the base of it anyway. What you're seeing here is that there's very different resistivity structure of this lava flow. The low resistivity values are basically mapping water. This is one of the classic techniques for mapping groundwater, is electromagnetic resistivity. And so you can see it here. Right? And it basically corresponds to these fractured areas of the basalt. The dense flow interiors don't have a lot of water. Okay, so this basically validates our model for how water moves through the lava flows. We can see that at a larger scale too, by looking at kind of the macro structures. And, if you drive from here to Eugene, you're going to pass by this thing called Lost Lake and this thing called Fish Lake, and they're kind of odd because they drain every summer. And we got curious about that, and we actually put out some sensors to measure the water depth in Lost Lake and Fish Lake, and combine that with some analysis of satellite imagery. And we're basically able to show here, this is what the lake drainage looks like at Lost Lake and Fish Lake. Drains every summer. Evidently it's drained a little bit earlier these days than it did a couple of decades ago, which is a climate change story. But the reason that they're draining is that they're both bordered by these young lava flows. And so this structure here, if you've ever been to Lost Lake, you can walk out in the middle of it, there's this big hole in this lava tube, and water is kind of just pouring into it. So during winter, when there's tons of snow, there's more water that can be sort of subtracted away, so you get a lake. But these so-called macro porosity features are kind of the reason you get this transient behavior. So in other words, you get these very odd hydrologic features in the central Oregon Cascades that come about because of lakes. Here's a little bit more on the hydrology. So just to show you in a little bit more detail, the average age of upstream bedrock is here when it's plotted into the longitude inland. It's just purely the age. And here's that yearly average change in discharge divided by the average discharge. And so the things that we're going to call springs are these things in blue, and they pretty much dominantly occur in the young bedrock, which is interesting. And I'm not going to talk about technologies because we're a little bit short on time, but what I will do is show you a cool compilation from here. This is hydrographs of all the river gauges that we use in this study. So if you kind of squint, probably small, in text, they will recognize some of these things. And some of them are very long records, like 60 years, something like that. Right? And the thing I'm going to call your attention to is that the green ones basically are these cases where the discharge doesn't vary at all. It's all constant. These ones where it goes from green to blue, seasonally it's changing, really constant. And so that's really what we mean by this change in hydrologic character. Last thing I'll say, last thing I'll say is that we're going to leverage these geothermal wells to tell a story about groundwater. Okay, this is what those geothermal wells look like. Here's a compilation of all of them that we used. And there's lots of crazy shapes on here, but the thing to call your attention to is these ones that are kind of sort of steep, basically vertical or even inverted. Bad news for geothermal resources, but great for groundwater because this is mapping out where the water is. And so we can go ahead and basically just take the length of these lines, percolate over. This is a map view representation of those three things. The larger the circle, the longer the isothermal region. And this basically maps out where groundwater is at present. So this, we have lots of different deep holes, you have bright rich hot springs here, etc. And plotted in another way, right, we can map this onto a volume of active groundwater that's responsible for sweeping the temperatures away. And if we do that and interpolate, it's pretty fuzzy. We don't have that many data points, but we have 75-ish. And we get a really large number. We get a huge volume of groundwater, sort of like 80 cubic kilometers, sort of actively flowing, and it's almost certainly the lower ground in the Oregon Cascades. That's similar in size to the nature continental lakes, 3 3 times the mean, 1 inch in Geneva, roughly half in Tahoe. A huge water tower, right, stored here at the top of the Cascade Range, which is really pretty interesting in a lot of ways. And we wrote this paper and there's done a lot of talking about that. So, it's fair. But yeah, I mean, thinking about water resources, thinking about why this area is special. I just told you a geologic story, but there's like clearly a human story and a climate story here that one could kind of dig into, and that's where we're going next. The last thing I'll just sort of say is that there's also, circling back to the volcanism, there's kind of a volcano story to this too, which is the youngest eruptions that have happened in this region came right up through this deep groundwater. They're the white stars, these Holocene eruptions, and they record a pattern that basically fingerprints water magma interactions, so like full circle based on this kind of like 2 mini fluids things. And so the style of eruptions that one sees in this region are also fundamentally shaped by water. And why is that important? Well, water and magma don't really like each other, and so you tend to get much more explosive eruptions when there's groundwater and magma interactions. And if you go to Sand Mountain, right, the reason it's called Sand Mountain is that it looks like sand. That's a phreatomagmatic texture. So it reflects the groundwater interaction. So it has pretty big implications for volcanic hazards, actually. Next eruption you have, there's a good chance that it might be phreatomagmatic character. And so, full circle, this critical zone influences the volcanic style as well. All right, so that's it. We got the cover of this Clear Fancy Journal, which I'm excited about. This beautiful spring Cascades. And I'll just sort of leave it up here. This is kind of the big takeaway. We get this state shift between the states and the critical zone. We found this big aquifer. I say found, but it's, of course, wasn't our discovery. We just sort of upgraded the number a bit. Obviously, we all know that there's a lot of water up here, but maybe you didn't know that there was quite this much. And so that's pretty cool. And then there's this thing about the volcanic hazards. With that, I'll stop and start to go a little. Happy to take questions.
Questions?
No. There's a lot of volcanoes here, but
Repeat the question.
the question was, are 80% of the world's volcanoes here? The answer is no. There are a lot of volcanoes here. I think the number is larger than one would expect based on, I guess, your sort of intuition from the big ones. So we have over 3,000 volcanoes that erupted in the last 2.5 million years. So far more than that if you look farther back in time. They've largely been eroded. But I guess it gives you just a sense of the scale.
For those of us that don't have a long attention span
Sorry.
or focus, is there an animated time-lapse production that would show us the development of the Pacific Northwest through all this volcanic activity, where we can kind of see, okay, in this year this happened, and this happened, this got created, that got created?
Depending on what you're interested in, kind of. There's some very coarse scale, like large scale, tens of millions of years scale animations of like the tectonic history. That's not going to necessarily tell you about when the volcanoes turned on and off. So I don't think something like that exists. Be a fun project. Yeah.
Yep. So back in 2002, there was a satellite recording of uplift at South Sisters. Is that still going on, or could you comment?
Yeah, still on. So South Sister, there was all this excitement, around the early 2000s. There was a little bowl, it's not the summit of South Sister, it's off to the side. Clearly of interest. USGS went out and put another GNSS, we call it now, GPS station out there. And what's interesting about it is that it's still ongoing, but it sort of wanes, waxes and wanes. It's never gotten quite as intense as it was in the early 2000s. Still ongoing today for sure. It's an intrusion that's happening in the mid-crust, about 6, 7, 8 kilometers depth. We're not super worried, but it's definitely a sign that there's active magnetism there.
Thank you.
Yeah.
Your amount of water was multiplied by porosity.
Correct.
If the water is removed, used, does the porosity drop, or is it still something that can be recharged?
That's a great question. Yeah, I guess. So that's been a huge issue in places like the Central Valley of California, right? Where basically you extract the groundwater and it compacts. Right? It's like San Joaquin Valley, or the famous photos of like huge amount of substance as the groundwater is being extracted. It's a little bit different up here, in part because the substrate is like a salt. It's a rock and not a sediment. And so, I get the short answer, I don't 100% know, but I don't expect actually that we would see the same thing, in part because the water is here hosted in fractures in a pretty coherent bedrock. And so most likely you wouldn't see a lot of substance or compaction in the fill it.
Bob, did you have a question?
Thank you. Your correlation between water and magma suggests that, and heat, that the more water there is stored in these fractures, correct me if I'm wrong, is it more likely that we would see a greater risk of volcanic activity? And is that activity based on the amount of water, or is it a combination of water, heat, and then movement of the Earth's mantle?
Yeah, right.
In other words, what's going to happen in the next 100 years?
Yeah.
And should I be worried?
We're excited. This is, I'm a volcanologist, so usually the question is like, what's the next eruption? And of course, I don't know. If I was to place a bet, I would always say Mount St. Helens, because that's the one that's erupting the most. Central Oregon, however, has got a lot of signs of activity. Right? We just talked about the South Sister thing, and that whole study we did where we compared all the geophysical sort of signatures of magma puts this region in a hotspot of sorts. Does that mean that there's likely to be an eruption? Not really, because the things that we're measuring are averages over things that are way outside of human timescales. So in some sense, like this is where I would expect an eruption. Will it happen in the next 100 years? Odds are not, actually, just based on the record of eruptions we had. The last one we had was about 3,000 years ago. And so, to your first question, though, I guess about the role of water. The water, you can think of it as like this little thing here. Yes, it's thick. It's circulates, and that's greater than a kilometer beneath Earth here. But where the magma is coming from is like 30 kilometers. And the things that are kind of responsible for its origin are much deeper. And so it's basically the last part of its journey is the interactions with the groundwater. And so I don't think it has much direct impact on when the next eruption will happen at all. What it might impact is the style of that eruption.
And seismically, if there is movement in the tectonic plates that result in earthquakes and subsurface movement, is that the trigger that we most likely would encounter that would then interact with water that's laying in that upper surface and that's cause a...
Yeah, I guess, so the first thing I mentioned when you talk about like the distribution of volcanism, you have this big change as you go from the northern part of Cascades to down here. Here we have what's called distributed volcanoes, all these little tiny vents, which is sort of unusual actually. they're what's called monogenetic, which means that they don't form these like long centers. They're kind of like one and done. One happens, and another one happens somewhere else. And they're kind of all over the place. Exactly why they do that is not super well understood. Definitely related to faults in some sense. And actually, one of the frameworks for understanding what the Central Oregon Cascade is that it's kind of like an extension of that like the background tectonic stresses are pulling it apart on both sides, even though we're in this subduction zone, which is very odd. But like it is this kind of extensional providence, meaning that like those structures, the thing that makes Green Ridge, for example, that's a big fault. Right up by Subtle Lake, that's a big fault. Those structures are super long-lived and have motion on them, and they represent sort of zones of mechanical weakness that magma exploits. So it's definitely those structures that matter. And then, of course, the water is sitting on top. And so again, that's really just the last part of its path. Yeah.
So do a couple more here, and then back there.
So in the last 100 years or so, human habitation is pulling more water more quickly out of the mountains. And has that affected what's going on upstream from where we live? And how so?
Yeah, I mean, it's a great question. I mean, in some ways, I think it's a thing that I actually would love to see you all tell people to figure out. No, seriously, right? Like, this is an understood perspective of hydrology. Like, I have some ideas, right? I don't think that the Cascades aquifer has been impacted by humans in a direct way. It's a massive amount of water. That 80 cubic kilometers is definitely an underestimate. And we have so much precipitation, so much, it's just this kind of staggeringly huge thing sitting beneath our feet. That's a different story, I guess, if you're down in the chutes and you're extracting groundwater for agriculture. But I'm kind of talking about the high Cascade stuff. It's kind of this like insane resource, but it's also not very well understood, and particularly the sensitivity of it. There was this sort of study that leveraged a particularly dry year. Dry is just low snowpack. It was 2015. It's a very low snowpack. And so same amount of precip total over the year, but almost no snowpack over the Cascades. And so that difference between snowpack and rainfall actually impacts the recharge of the aquifer in a pretty big way. And so that 1 year was used as a little bit of a case study to sort of like, hypothetically ask questions about climate change, right? That like you could hit, the projections certainly are to use snowpack in the Cascades over the next 100 years. And so like, did you see a change? And the interesting thing is that you didn't, actually, right? In 2015, no snowpack, almost zero, negligible change. And what that tells you is that it's a really big aquifer, right? And so that's interesting. But that's kind of like the only study that's kind of we've had. I would sort of wager that if you had 10 years like 2015, you would see a change, actually. And that's the study that needs to be done, this sort of sensitivity. Because, like we are basically going to be seeing changes. So you kind of like to know what to prepare for. I'm not sure that we know, actually.
Thank you.
Okay. You mentioned the quantity is equivalent to Lake Geneva.
Yeah.
So that's 21 cubic miles of water.
Yeah.
That's pretty good size of water.
Yeah.
So I have two questions. One, is it even engineering possible to tap the aquifer? And two, if we could, would we want to tap the aquifer? I mean, from a,
Sure.
holistic.
Yeah, no, I mean, it's a question. It's not a lake, I guess. Say that, right? It's not a thing you can like power your boat with. It's all about that water lives in fractures and pore space in rock, right? Like I used porosity measured in the drill holes to estimate the total volume. meaning that most of it is in these tiny little spaces. And so, right, tapping it, right, you can certainly do that, right, but it is a bit of a fundamentally different piece than thinking about it. And you know, those are. I sort of feel like those questions inevitably come up, right, when you start to consider just like the role of water in the West generally. In California, it's just like this huge thing. It's like the whole future is the future of water. And so here you're sitting on this amazing resource. The question is like, well, what to do? And, you know, in some sense, I feel like it is a thing that one must consider and think about the consequences of dealing with. You can't make management decisions about things before you know what's sensitive. And we just don't know that. And so I, you know, rather than answer your question, I'm sort of saying, like, I don't know, we got to figure out what's there before we can ask that question. Because what if the sensitivity is really great? You put a bunch of wells in and you kind of squander this resource. Right? That's the kind of the questions that we ask.
So there was a hand up right here, we're going to take two more, and that's it. We got to be respectful of Leif's time. We got to drive back to Eugene tonight.
I was curious about geothermal energy. Is there any commercial sites or quantity? You know, Iceland kind of runs their whole country on it.
Yeah.
In the United States, kind of use that type of technology.
Yeah, there's, you know, there was a lot of interest in this in the 80s and 90s. So all these holes were plugged in. And then, you know, where there was particular interest was actually the rain curtain. And the rain curtain thing, among other factors, sort of delayed that. But it's still on the table. And Newberry is, in fact, one of the national sites that's been looked at. It's definitely viable.
Newberry has two lakes at the top. One is east and the other is Paulina.
Yeah.
Over the last 10 years, the water level was pretty stable at both of them. I believe east was about 15 to 20 feet higher in terms of elevation. About 4 years ago, east started to drop. It's dropped about 17 feet. Paulina has maintained the same elevation. I've heard some people, like with the Deschutes forestry, said that it was because of drought. Then I heard somebody say it was because of perhaps volcanic activity. A fissure opened up and dropped it. Once it dropped, it hasn't changed over the last 3 years. Why?
That's cool. I didn't know that. That's interesting. Yeah, I mean, I guess, right, so the considerations, if it's abrupt like that, it's likely not drop. There are structural changes that can happen. Need not be necessarily directly volcanic, but like we live in a very active place. It's quite exciting, right? There's faults all around. There's volcanism. We've got lots of stuff going on in the solid earth beneath Earth. And so my sort of guess would be to think about faulting in the shallow crust, and you'd probably see a signature of that. And this is a place that's pretty well monitored, so that's a testable hypothesis. Probably, I feel like I might have heard about it if it was actually a big event. And so maybe it's something a little bit more subtle. But yeah, that's cool. I didn't know that. And there's a lot of mysteries. I guess I mentioned very briefly that study of the lakes.
I know there are hot springs at both of those lakes. The ones at east are a little more active.
Yeah.
You really smell the sulfur, so on and so forth. But
yeah, well, Newberry's got a lot of activity going on. You can, in fact, we'll talk about Newberry. You can image the magma reservoir in Newberry quite well. It's sitting there, it's doing its thing. So yeah, I mean, somebody should look at that. Yeah. Sorry, I can't explain that.